All right, so here we're going to talk our way through diagonalizing using eigenpairs. So what does it mean to diagonalize a matrix? This may be a first pass. So to diagonalize a matrix, what I mean is that there's a matrix A that I'm starting with, and then I can do some kind of an adjustment to that matrix A. So in my case, that's going to be, I'm going to multiply it before and after by a matrix here. So I've got a matrix X and a matrix X inverse. So I'm multiplying before and after A. And what I'm going to end up with here is a matrix called capital lambda. This capital lambda is going to be a diagonal matrix. This is going to make my life a lot easier, especially when I'm like trying to raise something to a power or trying to raise something to lots of powers. Having a diagonal matrix is just a lot easier to deal with. So this is a goal for me. So we're going to try to make this happen. And it's actually going to be relatively straightforward. It doesn't take much, strangely. So I'm going to construct a couple of matrices. So I'm going to construct a matrix X and a matrix lambda. And the way I'm going to construct those matrices is I'm going to go ahead and I'm going to say, like, look, let me assume that I can find a whole mess of eigenpairs. So I'm going to assume, oops, that's a bad spot to put that. Let's put it up here. I'm going to assume we can find n linearly independent eigenpairs. So I'm going to say that eigenvectors are linearly independent because that's the kind of thing that can be linearly dependent or independent, right? It's a set of vectors. So those linearly independent eigenvectors, though, are going to have eigenvalues associated to them. So I'm just going to give them names, right? I'm going to say I've got lambda 1 and x1. I've got lambda 2 and x2. I'm going to say I've got lambda 3 and x3. And kind of so on, right? Till we get to lambda n x to xn. Now, I've said before that there might be repeated eigenvalues. That's totally fine here. It's also going to be totally fine here if my eigenvalues are complex. Like, I'm just going to deal with that. In most of the examples I'm going to show you, they're going to go ahead and be linearly independent. They're going to be, the vectors are going to be linearly independent, and the eigenvalues are going to be distinct and real. Doesn't have to be that way. We can make do as long as we can find enough eigenvectors. So there are going to be matrices for which I can't find enough eigenvectors. This is not one of them. So I'm going to construct this big matrix capital X by sticking the eigenvectors into it as column vectors. Right, so I've got x1, x2, and so on, right? Here at the end, I'm going to end up with xn. And then I'm going to construct my matrix lambda. This is going to be my diagonal matrix. It's going to be a couple big fat zeros in the top and bottom corners, right? And then it's going to be lambda 1, lambda 2, and so on until we get to lambda n down here. So it's the lambdas down the diagonal, and these lambdas have to be in the same order that the x's are in. And then I'm going to go ahead and look at, we're going to consider. So this is me saying that I'm defining this. Oh, that's going to be a problem. Let's do that this way. Just want to scoot this over a tiny bit. That F minus Joe. Okay, let's try our lasso select one more time. Okay, and then we just want to scoot that over here. So I'm saying define x and lambda, and then we'll consider do a to x and also do x times lambda. Okay, so if I do a to x, right, I know that I'm going to get a new matrix that's going to have ax1 in the first column. It's going to have ax2 in the second column. and on until I get to AXN in the final column. Then I'm going to know, because AX1, well, X1's an eigenvector, and it goes with the eigenvalue lambda 1. I know that that first row is going to be lambda 1 x1. Sorry, first column is going to be lambda 1 x1. Then the second column is going to be lambda 2 x2, and so on, until we get to lambda n xn. Right, so that's all my this is my AX matrix. I got the eigenvalues with their associated eigenvectors here as columns. Now here when I do this multiplication, this is going to be me multiplying this matrix, right? So I got x1 here, x2 in the next column, and so on until we get to xn. And then I'm multiplying this by, oh, what am I doing? Silly Joe. Silly, you're using a computer. You can just copy and paste that thing. Okay, so I'm going to pick up that first column of lambdas. I'm going to go ahead and do that multiplication, right? And as I do that multiplication, I'm going to notice that what I get here is I get that exact same lambda 1 x1 for the first column. Then I'm going to get lambda 2 x2 for the second column, and so on. Right, so a little matrix multiplication is going to tell me that A capital X is equal to X capital lambda. And this is the trick. This is me done, actually. As long as I know that X has linearly independent columns, which is what I assumed here by having linearly independent eigenvectors, then I can invert that matrix. So I'm going to go ahead and do that, right? So I'm going to invert that matrix to the other side. I'm going to get X inverse A, X is my capital lambda, and that's it. I've diagonalized this matrix. This is going to make my life really, really chill. So this gives me a way to diagonalize the matrix that I had as my example in the previous thing here. So my example in the previous was I was looking at this matrix. So I was looking at 3, 2, 1, 4. And I got here these eigenpairs. Right, so I'm just going to grab these and bring them over. So here's my example. I'm going to diagonalize. And I can't spell diagonalize, so you'll have to forgive me there. And the matrix I'm going to diagonalize is 3, 2, 1, 4. And so I went and I found the eigenpairs already. So there's one, and here's the other one. Okay, so those are my eigenpairs. So the way I'm going to diagonalize this matrix is I'm going to say, all right, I'm going to put 1, 1, negative 2, 1. That's going to be inverted times 3, 2, 1, 4 times 1, 1, negative 2, 1. And this is going to give me the diagonal matrix. And here's the only part of this that's hard. You just have to be sure that this vector here gets its associated eigenvalue in the right spot. So because the first column was 1, 1, and its associated eigenvalue is 5, the 5 has to go first. Then in this second slot, I can fit that too. So that's it. That's all there is. If I wanted to write this the other way, so this is me writing X inverse A X equals lambda, right? So this is two matrices that I can use to turn A into a diagonal matrix. I can also reverse that process. So this is the exact same thing as saying A is going to be, and I need to multiply X inverse from the right-hand side and X from the left. So these two are my diagonalization methods, right? As long as I can find enough eigenvectors, this is easy peasy. I can do this. We should probably have an example of a matrix where I can't do that. So I'm going to go down here a bit, and I'm going to write a non-example. So here's my matrix that's a non-example. 0, 1, 0, 0. You may recognize this matrix. I'm hoping that you're calling this one tape up and forget. Right, this is the matrix that maps xy to the vector y0, right? So I'm like, I think this should be doable, right? So I'm like, okay, so what are the eigenvalues? Let's go find those first. I should be able to find those always. Okay, so to find the eigenvalues, I'm looking at the matrix here minus lambda I. So that's going to be a minus lambda, a 1, a 0, a minus lambda. Okay, then I'm going to calculate the determinant of that. And so I'm going to get lambda squared minus 0. That's just lambda squared. Okay, so the solutions to setting this determinant equal to 0 are lambda is 0 and lambda is 0. All right, cool. So now I'm going to look at the null space of this matrix. Right, so I'm going to take my matrix here, 0, 1, 0, 0. I'm going to augment this by 0. I'm going to row reduce. Right, I already did that. I'm going to get y is equal to 0 and x can be anything at all. Okay, so if y has to be 0 and x can be anything at all, I'm going to put this down, right? Like, this is me solving a null space. The null space of this thing is one-dimensional. Here's a one-dimensional, like, here's a vector. Okay? So I ended up with this as my eigenpair. And the trouble is, I should have my other eigenvalue, right, 0, and I should be able to find another vector here. I can't. This matrix doesn't have a two-dimensional null space. It has a repeated eigenvalue, but it doesn't have enough null space to make up for this. This just can't work. This is a matrix where I cannot produce a second linearly independent eigenvector, even though I have two eigenvalues. Just can't do it. It's gonna kind of sucks. Like, this is how it looks when you can't produce that other eigenvalue or eigenvector. It's there. Like, I can't diagonalize this. Like, that's it. Sorry. No can do. All right. Thank you guys for looking. Much appreciate the watch. See you later.